Okay, welcome back everyone. So in this video we'll talk about matrices, cover some of the basics and when and why do we use them. So matrices are really just a notation for representing systems of linear equations, a very convenient notation in fact. And they live in a correspondingly named area of mathematics called linear algebra. Now, there's a few different ways or viewpoints you could take on matrices. As physicists, though, we're primarily concerned with how matrices encode transformations and operations on vectors and vector spaces. So yes, these transformations do become very important. Now, we've been dealing with standard 2 or 3-dimensional vectors and then vector fields. But much of physics is built upon more abstract notions of vectors and vector spaces. So your regular 3D vectors in relativity are going to become 4-dimensional vectors, 4 vectors, which are you can think of as vectors in space and time. And yes, matrices are going to act upon those types of vectors. Quantum mechanics is really the big area for matrices, though. So in quantum mechanics, the quantum state, psi, is a type of complex vector that lives in a complex vector space called a Hilbert space. This is this is Heisenberg's original 1925 paper, in which he introduced the new formulation of quantum mechanics, which is the more modern formulation of quantum mechanics, and yes, that's based upon matrix equations. So matrices we should try and think of as transformations or operations on vectors and vector spaces. We'll do plenty of examples of how this works over the next few videos and over the next couple of weeks. But let's just define the action of a matrix upon a vector. So a matrix M, we would usually write matrices as uppercase Latin letters. They don't usually go in bold. Now, we could write the elements of a matrix, Mij. Just be wary that this is a single number here, Mij. It's the ijth element of M, whereas the matrix M is really many different elements altogether. And so we can act the matrix M upon a vector V, so M just acting straight onto V, as follows. Now, I've supposed that the matrix M is a 3x3 matrix, so 3 columns, 3 rows, 1, 2, 3, 1, 2, 3, and that's acting on a 3-dimensional vector. Now, in order to calculate how it acts, we first work through the top row, and we multiply every element in the top row by every element in the vector. So you're going to get m1 times v1, m12 times v2, m13 times v3, and add those all up and they all go in the top element. Then, let me display that. Okay. Then we'll have the second row, and we do the equivalent steps, right? So m21 times v1, m22 times v2, m23 times v3, and the result of that goes in the second row. And finally, you can tell what's coming. The final row, m31 times v1, m32 times v2, m33 times v3, and the result of all of that goes in here in the final row. This is just it looks like a matrix. It's not a matrix because this is really just a vector. It's some number, some number, some number. Although you could think of a vector as a special type of matrix. Okay, so let's just perform one example calculation. So firstly, 1 times 1 plus 0 times 0 plus 2 times 2. So that's 1 plus 0 plus 4, which is 5. Then 3 times 1 plus 1 times 0 plus 0 times 2, which is 3 plus 0 plus 0, so 3. And then minus 1 times 1, 2 times 0, minus 1 times 2, so that'll be a minus 1 and a minus 2 adding up to give you minus 3. We could write the matrix equation down in terms of its elements like this. Occasionally that's useful, but it means exactly the same thing as m times v. Now, this matrix maps a 3D vector, so this vector, onto another 3D vector. And that's going to be the case of any matrix which is square. So as long as you have the same number of rows as columns, then you'll map an ND vector onto another ND vector. But we could also imagine matrices that could map into like lower or higher dimensional vector spaces. So if we've only got 2 rows instead, we'll map to a 2-dimensional vector. And so 1 times 1, 0 times 0, 2 times 2 is 5. 3 times 1, 1 times 0, 0 times 2 is 3. And you see that we've run out of rows at this point. So we end up really with just a two-dimensional vector. We could instead have 4 rows, in which case we just carry on down. Those two elements are going to be the same as these ones because the top 2 rows are the same as that. Then we'll get minus 1 times 1, 2 times 0, 1 times 2. So that's minus 1 plus 2, so 1. Yep. And then 0 times 1, 1 times 0, 2 times 2, so 4 in the bottom. So in that case, we get a 4-dimensional vector out. So I guess you'll have noticed this already, but in order for the product to work, then the matrix needs as many columns as the vector has rows. So if we were to try and act a matrix like this, so 1, 2, 3, 4, 5, 6, then trying to perform that, we'd get 2 times A, so 1 times A plus 2 times B plus 3 times, and then we've run out of components in the vector to multiply. So expressions like this don't make sense. The matrix needs as many columns as the vector has rows. Okay, so a couple of examples. So firstly, there's the identity matrix, which acts like the number 1. And so it leaves the vector unchanged. Now, identity matrices are always going to be square, but you can have them in different numbers of dimensions. So this is a 3x3 identity matrix. They're always filled with zeros apart from the diagonal, which is filled with 1s. And you can see what's going to happen. The 1 will always just pick up this here. This middle row, because there's only a 1 there, will just pick up whatever's in this row. In this case, it's a 0. And finally, the 1 here will just pick up the third component of the vector, so a 2 there. We can multiply matrices by scalars, in which case, if we multiply the identity matrix times the scalar A, then we'll get a matrix like this. And you can see that all that is going to do is take any vector and just stretch it out by a factor of A. So you'll get A, 0, and 2A. So yes, any matrix like this will just take a vector, and every single vector you act it on will just be stretched by a factor of A. We could form matrices like this, for instance. Now, all that one's going to do would be to reflect the x component. So that'd be like reflection in the yz plane. Or we could have minus 1, minus 1. Minus 1, which is just the negative of the identity matrix. In which case, that's going to just invert every vector for its negative. Okay, another type, which are going to come up very regularly, are these. These are called rotation matrices. So this is a 2D rotation matrix. And so that will take any vector and rotate it through an angle of theta. Now, I haven't written that out explicitly here, but let's do that. So we'll get the cosine is going to multiply the x, so x cosine of theta. And then the negative sign is going to multiply the y, so subtract y sine of theta. And then in the second row, sine theta times x. So x sine theta plus y cosine of theta, like that. Okay, so this is just the same vector, but rotated through an angle of theta. Okay, so now matrix multiplication. So I already hinted above that we can multiply any matrix by a scalar. Now, if you do that, then every single element inside the matrix gets multiplied by that. We can add two matrices together as long as they're the same shape. If they're not the same shape, then the addition isn't well defined. So if we do add them, two matrices of the same shape together, then all the components add individually. So you will have A plus E, B plus F, C plus G, D plus H. Now, the one you want to get used to is matrix multiplication. And we kind of did a little bit of that already. But in addition to multiplying matrices by vectors, we can also multiply matrices between each other. So matrix times matrix. Now, in order to do that, it's a very similar process to the one that I showed you above. So firstly, work along the first row and we'll work along the first column. In which case we'll get A times E plus B times G, like that. Then we can work along this second column of the second matrix, in which case we've got A times F plus B times H. Then we can work along, the bottom row of the first one and the first column of the second one, in which case we get C times E plus D times G. And then finally, those two. So C times F plus D times H. That. So let's go ahead and perform this calculation. So out of this, we'll get a 3 by 3 matrix. So in the top, we get 3 times 0, 0 times 2, 1 times 0. Altogether, that is 0. Okay. Then sticking with the top row, but working down this column, 3 times 1, which is 3. 0 times minus 1, 1 times 1, so that's going to be 3 plus 1, which is going to give us 4. Then finally, sticking with the top column and this one here, 3 times 0, 0 times 0, 1 times minus 1, so we'll get minus 1. Now let's go to the second row. So second row, first column, 0 times 0, 1 times 2, 2 times 0, which is 2. Now the second column, second row, so 0 times 1, 1 times minus 1, 2 times 1, so that'll be minus 1 plus 2, so just 1. Then again, sticking with this row, and in the final column we'll get 0 times 0, 1 times 0, 2 times minus 1, so minus 2. Then finally the bottom row, 1 times 0, 2 times 1 times 0, 0 times 2, minus 1 times 0, they're all 0. Then final row, second column, 1 times 1, 0 times minus 1, minus 1 times minus times 1. So that's plus 1 from these two and minus 1 from that, so they cancel. And the very final element is minus 1 times 0, 0 times 0, minus 1 times minus 1. So altogether that gives us 1. So like that. So we write the product of two matrices simply by putting them next to each other. So AB, like that, implies the product. There's no special symbol we need. In terms of the elements, we can write out the equation like this. Now, it's useful to remember that sometimes, at least I find it difficult to remember which way around the rows and the columns are labeled. The way I remember it is by remembering that when you take the product of two matrices, when you matrix multiply, then it's the inner index that gets summed over, like this. And so we're summing over the j's, and so because when we walk along like this with the first, and we walk downwards with the second, so the j there, the second index is referring to the column, because first column, second column, third column, and the first index is referring to the row, so first row, second row, third row. And then, yes, we'll get a matrix. A times B is a matrix. This is what it is. And that will refer to the ith component. Okay, so matrices can be different shapes, but in order to for it to make sense, then the number of columns in the first matrix must equal the number of rows in the second matrix. So this one does make sense. So we can work along here and here. So A times G plus B times I. Then here and here. A times H plus B times J. Then, let's see. Then let's work along this row. So C times G, D times I. CG plus DI. CDHJ. So CH plus DJ, and then we can keep going down. So E times FG and E and FG and I will give us E times G plus plus F times I, and then the final element will be E times H, F times J. E times H plus F times J. And so out of this we get a let's see, that's a 2x3 matrix. Okay, so the product of an L by N matrix with an N by M matrix is an L by M matrix. And a couple of final properties. Matrix multiplication is not commutative. If you switch the order of A and B, you're going to get something different in general. So yes, matrices do not commute when you're multiplying them, but they are associative. So if we multiply B times C and then multiply on the front by A, then we get the same thing as multiplying A by B, then multiplying on the back by C. So that does work. Okay, we'll leave this video there.